Good afternoon. Just picking up where we have been working with logarithmic equations, and we have from the test 4 review set. Okay, and we have just items that we have in the set. Okay, we have with number 14. Again, I had mentioned there was a typographical error, and where the 2's on the left were supposed to be logarithmic bases. Okay, and just for what we have in this problem. Okay, so we're looking at the difference of base 2 logarithmic terms. Okay, again, so we have the base 2 logarithm of x plus 7 minus the base 2 logarithm of x plus 1, okay, is equal to 2. All right, and just looking at what we have in trying to attain the value or values of what we have for x. So just kind of just setting things up and looking at what we have for our properties concerning logarithms. Okay, that might be a benefit in terms of solving logarithmic equations. And again, we have for y is equal to the base a logarithm of x. Again, the logarithmic base is going to be a positive value with the exception of 1. And whatever attachment we have, we want to ensure that we have a positive value. Okay, so we have for our logarithmic terms, we have a is represented by 2. And for the attachments representing x, in each of these we have x plus 7 as well as x plus 1. And looking at what we're going to have for x, we want to ensure that both x plus 7 and x plus 1 be positive. Okay, so we'll have x plus 7 and x plus 1 must both be positive. All right, and looking at what we have in solving for x. So right now we have difference of logarithmic terms, and what I can do is revert to the sums and differences of logarithms. And we're going to be looking at combining the logarithmic terms as a single entity. Okay, and where we had expansion as well as the contracting of logarithmic terms, we've had multiplication and addition to imply each other, and we've also had division and subtraction to also imply each other. And for the difference of logarithmic terms, once I combine, okay, I can write in terms of division between the attachments. So looking at combining as a single base 2 logarithmic term, so we have a base 2 logarithm, and we'll have in the ratio, okay, so we have for x plus 7, okay, this comes from a positive logarithmic term, so we'll have x plus 7 to belong in the numerator. And with x plus 1, since that is the attachment of a negative base 2 logarithmic term, then we'll have x plus 1 to go in the denominator. And so we have in the rewrite, we have the base 2 logarithm of x plus 7 over x plus 1 is equal to 2. And looking at expressing what we have in the variable x, okay, all right, so we have the base 2 logarithm of x plus 7 over x plus 1 is equal to 2, and I can revert to the elimination of the presence of the base 2 logarithm on the basis of taking the property of logarithms, whereupon I have a to the base a logarithm of x is equal to x. Okay, so how do I follow through with this property concerning number 14? Okay, well, with what I have in this step, I can treat both sides of the equation as powers to which the matching exponential base will be raised. Okay, so matching the logarithmic base 2 is going to be the exponential base 2. So we have 2 raised to the base 2 logarithm. Can I have of x plus 7 over x plus 1, okay, and I have is equal to 2 raised to the second. Okay, and in utilizing, okay, the exponential base 2, so 2 to the base 2 log of x plus 7 over x plus 1. Okay, this will go to x plus 7 over x plus 1. And we have is equal to 2 squared, okay, which is 4. And looking at undoing the fraction, okay, so we have upon multiplying both sides by x plus 1, okay, so we're going to have x plus 7 is equal to 4 times, okay, the quantity of x plus 1, and we have upon following through, so we have x plus 7 is equal to 4x plus 4, and we have with like terms on opposite sides of the equation. Okay, so I can combine the variable terms, okay, and I'll just take out the smaller x term, though I could take away 4x from both sides, but if I subtract x, so we'll have that 7 is equal to 3x plus 4, and we have upon following through, okay, so if I take 4 away from both sides, okay, so I have 7 minus 4 is 3, yeah, 3 is equal to 3x, and with division by 3, okay, we'll come out to 1 is equal to x. And so we have for the stated solution, okay, we have that x is equal to 1, and just double checking what we have now. Okay, so we have with x at 1, and again, the attachments and the original setup, okay, must both be positive. Okay, so with x at 1, 1 plus 7 is 8, that is positive. And 1 plus 1 is 2, also positive. So 1 will fit the bill of being the solution. Okay. Now, for what we have still working with logarithmic equations, and we have for item number 16, our next one, okay, so we got a single logarithmic term, and this is going to be in base 4. So you have 2 times the base 4 logarithm of the quantity of x minus 2 is equal to 6. And again, whatever I have for x, whatever I have for x, I want to ensure that x minus 2 be positive. All right, and to start things off, okay, now we got the coefficient 2 times the base 4 log of x minus 2, and again, whatever I have for x, I want to make sure that x minus 2 be positive, and we have this term is set equal to 6, and what I can do to sort of simplify the problem is to eliminate the presence of 2 by dividing. So I can just write this as the base 4 logarithm of x minus 2 is equal to 3. Okay, so we got with, again, division by 2. Right, so we have the base 4 logarithm of x minus 2 is equal to 3. Right, so I have a logarithmic term, and again, I can undo the presence of the logarithm if I treat both sides of this equation as powers to which the matching exponential base will be raised. Now before number 14 I used the exponential base 2, and now in number 16 with the base 4 log, I'm going to now apply the exponential base 4. So we had 4 raised to the base 4 logarithm of x minus 2 is equal to 4 raised to the third power. So for what we have on the left, again, we have x minus 2. And we have 4 to the third, which is going to be 64. And we have with x minus 2 equal to 64, and we have that x is equal to 66. Now I can go back. If x is 66, 66 minus 2 is 64, and that'll be positive. So we do have a solution, once again, for x with the number 66. All right, and in continuing with what we have for logarithms, and we now have, in the case of number 17, we have that 7 is equal to the base 3 logarithm of the quantity of x squared plus 162. And with what we have in this problem, okay, so you have with 7 equal to the base 3 logarithm, again, of x squared plus 162. And for this one, okay, have a single base 3 logarithmic term. And what I can do now is to eliminate the presence of the base 3 logarithm. If I treat both sides of the equation as powers to which 3 will be raised. So in this case, we're going to have 3 to the 7th is equal to 3 raised to the base 3 logarithm of x squared plus 162. So we got 3 to the 7th. Okay, so this will be 2187. A lot of 3's involved. And we have on the right hand side, okay, we'll have x squared plus 162. And in looking at setting up things for x, okay, what I'm going to do here, I got x squared plus 162 equal to 2187. And I think I'm going to isolate the x squared in this one. Okay. So I'm going to take 162 away from both sides. And here we have for the difference between 2187 and 162, this will be 2025. So 2025 is equal to x squared. And just reversing the order with the commutative property of equality, again, like going from b is equal to a is equal to b format. Okay, so with x squared equal to 2025, okay, I can apply the square root property of equality. So in this one, as I go from x squared to x, we'll have this set equal to plus or minus the square root of 2025, and 2025 is a perfect square value, and there will be two numbers that will square into 2025, and those will be negative and positive 45. Okay. And just looking at what we have in checking, okay, so for x squared plus 162, again, we have that is the attachment, and x squared plus 162 must be positive. And again, with negative and positive 45, square of a negative is a positive, square of a positive is a positive, and if I add 162, okay, I'm still going to have a positive result. So both negative and positive 45 will qualify as solutions to what we have in this particular problem. All right. Now, and what we have with the remaining logarithmic equations, and we have in the case of number 18, okay, so now we have a natural logarithmic term, and that is set equal to 0. Okay, so right now for what we have in number 18, okay, so you have the natural logarithm of x squared minus 4x plus 4 is equal to 0. And looking at what we have present, so just looking at setting things up here. Okay, so for whatever I get for x, again, I want x squared minus 4x plus 4 to be positive. All right, and again, just a reminder. Now, again, we have a single logarithmic term, and I can free up x squared minus 4x plus 4. And keeping in mind that a natural logarithm will be a logarithm of base e, again, where e is that 2.718 figure. And for what I have here, okay, so I have natural logarithm is a logarithm of base e, and I can eliminate the presence of the logarithmic notation, applying them both sides as powers to which the matching exponential base will be raised. Of course, that exponential base will be, once again, the letter e. So here we're going to have e to the base e logarithm of x squared minus 4x plus 4 okay, we have is equal to e to the 0. So we have on the left, okay, we have x squared minus 4x plus 4, and for e to the 0, now a non-zero value raised to the 0 power is going to be equal to 1. And so we have the formation of a quadratic equation. And if I take what I have and express in standard form, so I can take 1 away from both sides, so I have x squared minus 4x plus 3 is equal to 0. And in looking at what we have now, okay, we have a trinomial that can be factored, and establishing what we have. Okay, so for x squared minus 4x plus 3, so we have with the factors, we have x minus 1 as well as x minus 3. And setting each of the factors to 0. Okay, so we have for x minus 1, we're going to have the x is equal to 1. And for x minus 3 equal to 0, we're going to have the x is equal to 3. And going back and checking. Okay, so I want x squared minus 4x plus 4 to be positive. So here we have 1 squared. Negative 4 times 1 is negative 4. 1 minus 4 is negative 3. And we have in turn, negative 3 plus 4 is 1, which is positive. So 1 is going to check out. And for 3 squared is 9. Negative 4 times 3 is negative 12. 9 minus 12 is negative 3. And again, we have in turn, negative 3 plus 4 is 1. So with 3, the attachment is also positive. And so x, again, is going to have 2 solutions with 1 and 3. Yes.
So I get that the answer x could be 1, but I thought you said that the attachment also could not equal 1. But
No.
if you,
Okay, let me put this. Okay, what in terms of what cannot equal 1, it would be we're looking at the base, the logarithmic base and the exponential base. The attachment can be 1, but the whatever half of the logarithmic base and the exponential base, that cannot be 1. And that, so you have like your base, say, logarithm, okay, it is positive, but it cannot be equal to 1. Now the attachment can be 1, but the base, whether it's logarithmic or exponential, an exponential function as a 1-to-1 function, that cannot be 1.
Okay, I'm sorry. I was super confused.
Okay. Yeah. It's just yeah. What it was is just yeah. So the attachment is distinct from the logarithmic base. It is in other words, that which represents a in this case cannot be 1. That's what that is. Yeah. Right. Now, for what we have in the case of number 19. Okay. Now we have in this setup. Okay. Now we have the sum of logarithms. Okay. In number 19. Okay. And for this one. Okay. So you have a base 3 logarithm of x plus the base 3 logarithm, okay, of the quantity of x minus 8 is equal to 2. Okay, and so for what we have in this setup, okay, so we have 2 logarithmic terms in the mix. Okay, so whatever I have for x, okay, in other words, okay, for x and x minus 8, okay, both of these must be positive. Right, so here we have the sum of base 3 logarithmic terms. And we had from the first problem today, we looked at a difference of logarithms. Okay, where we had the subtraction to be converted to the operation of division between the attachments. Okay, now I have at the other end of the spectrum, I have the sum of logarithms, and we're going to have that addition will imply multiplication. So once I consolidate in the base 3 logarithm as a single term, so we'll have the attachments x and x minus 8 to be multiplying each other. Okay. So you have the base 3 logarithm of what's going to be x times the quantity of x minus 8 is equal to 2. Now you just go ahead and distribute x over x minus 8. Okay, so this is going to become the base 3 logarithm of x squared minus 8x is equal to 2. And now looking at what we have now. Okay, so with the sum and difference logarithmic properties. Okay, so I've gone from 2 logarithmic terms to 1, and now I can eliminate the presence of the base 3 logarithmic setup upon treating both sides at this stage to powers to which the exponential base 3 will be raised. Okay, so I have 3 to the base 3 logarithm of x squared minus 8x is equal to 3 to the second. Okay. So we have on the left hand side, okay, we're going to have x squared minus 8x is equal to 9. Okay, so I have another quadratic equation that is set up, and if I put this in standard form, okay, so I have x squared minus 8x minus 9 is equal to 0, and looking at factoring, okay, so factors we're going to have here, we'll have x plus 1 and x minus 9. And utilizing the zero product property, if I have the x plus 1 is equal to 0, I'm going to have the x is equal to negative 1. And if x minus 9, okay, is equal to 0, I'm going to have the x is equal to 9. Okay, and now just checking the results. Okay, now again, x and x minus 8 must be positive. Okay. With x at -1, guess what? We got base 3 logarithm of -1. X is negative, so for what we have here, -1 is going to be disqualified. Now for what we have in the case of 9, okay, we have the base 3 logarithm of 9, 9 is positive. We have plus the base 3 logarithm of 9 minus 8. 9 minus 8 is 1, okay, and that is going to also be positive. So 9 checks out. So in this problem, okay, there is one solution, and that is going to be with the number 9. Okay. Now, looking at what we have, going back to our business math items, okay, there was a part I had mentioned in brief about annuities, and we had just looked at an annuity from the vantage point of the traditional use of the annuity formula, and that is like for what you would have, or in most cases be regarded as the minimum or the conservative estimate for the final balance. And we have, for the case number 26, okay, we have a two-part annuity problem. Okay, and part A is asking for the minimum future value, whereas in B it's asking for the theoretical maximum value. And for these cases, okay, now we have Ray, who is planning on retiring in 15 years, and his plan is to contribute $1,000 to an IRA on a semi-annual basis. And it says that the rate of return is assumed to be 10% compounded semi-annually. So you had the frequency, the contributions, and the compounding of interest to be on a semi-annual basis. All right, and just for what we have in the setup for this annuity, okay, so just like with the non-continuous compounding algorithm, okay, we have, again, so you have your P is going to be what is invested or contributed. Okay, so P is at $1,000. And the frequency of the contributions as well as the compounding of interest, okay, we have N is equal to 2. So we're looking at things done semi-annually. And for the rate of interest, okay, so we have at 10%. And this will be recorded as a non-percent decimal. And for the time span, okay, we're looking at 15 years. Okay. And for what we have in the case of Part A, okay, it says what would be the minimum value of the IRA, okay, with this plan. So we have, in the case of the minimum, and this will be utilizing, okay, the regular annuity formula. And again, we have that A is equal to P times the quantity. Okay, now we have 1 plus R over N to the N times T, kind of like with your regular future value problem. But with annuity, you're looking at repeating contributions, so you're going to have a bit of an augmentation of the regular compound interest formula. Okay, so you have this layout for the annuity, and looking at the numbers we have. Okay, so you have the principal P is at $1,000. And for 1 plus R over N, so R we have at 0.10. We have that N is at 2. Then we have, in terms of the exponent, okay, so 1 plus 0.10 over 2 and to the n times t degree. So n is at 2, and t is at 15. Now minus 1, you have times n over r. So n is at 2, r we have at 0.10. Okay, so the only thing I've done is just substitute for p, r, n, and t with the corresponding numerical values. Okay, so right now, so you have $1,000. And for the numbers inside the brackets, okay, so you have for the sum, we have 1.05. And for the n times t, power 2 times 15 is 30. You got minus 1. Now n over r, you have 2 over 0.10, and that is reducible to a whole number at 20. Okay, so with the remaining activity so far, okay, we have 1.05 to the 30th. Okay, and this is going to be a decimal, and just for what we have among the first digits. Okay, so we're looking at 4.3. So yeah, 4.3219 from 1.05 to the 30th, and I'm going to deduct 1. We have times 20. Okay, so you still have $1,000 waiting, and you have times the difference. Okay, so you have among the first digits, have 3.321942, and just let the calculator result fully show. And once you multiply this difference by 1,000 and also by 20, you're going to have the minimum value of the IRA to be right at, in this case, $66,438.85. Okay, so the traditional annuity formula, okay, this is like in the case of the conservative estimate, which you have to be the minimum. Now, for what we have in the case part B, okay, it's asking, yes.
I'm sorry, before you move on to that next part. So the only thing I'm confused about is in the problem, it said he puts in $1,000 every 6 months, right?
Correct.
And it's compounded semi-annually. So does n being 2 account for the fact that it's being compounded and he's putting in an extra 1,000?
Correct. In other words, for that formula to work, it's like the frequency of the contribution and the frequency of the compounding will be the same.
Okay.
And for this one, okay, the reason I'm saying minimum, it's like the theoretical minimum would be like the contribution would be like at the. In other words, it's like in terms of application, think of it like this: if the activity were to say, if the financial activity theoretically started like January the 1st and ended December the 31st, it's like the minimum would be like he's putting in the $1,000 like last day in June the 30th, and the next $1,000 would be put right at the end of the year. In other words, it's like, in other words, there's activity going on between, the 1st of January to the end of December, where he's not made that $1,000 contribution. So it's kind of taking away any potential interest that is being accrued. But on the maximum side, if he contributes at as close to January the 1st as possible, he's got that $1,000 plus some interest being drawn by the time he gets to the end of June and the 1st of July, where he's going to make his next installment. Okay, so in other words, it's like, say if he were to wait until the end of June before that first $1,000 contribution, there's no interest going on that's being added. but by contributing at the start of the year, he's got that $1,000 in play and interest that's going to be drawing for 6 months. And this is where the maximum is going to come in. So in terms of the theoretical maximum, how this is going to be different. If we were to have put in the $1,000 at the start, let's say of the 6 months, okay, now you're going to have the same formula, but there's just one added dimension. No, it's not this formula. Okay, so you got the compound interest along with the other activity that defines the annuity. Okay, so you got this part here, but what is going to add a bit of an added layer where the maximum is going to come in is that you got the annuity formula times the quantity of 1 plus R over N. That's the only difference. Okay, so we have in the formula. So you got the annuity formula times 1 plus R over N. So multiplying by 1 plus R over N. This is going to arrive at the theoretical maximum. And guess what? For 1 plus R over N, you're looking at 1 plus, and your R is at 10%, and N is at 2. And guess what? Everything else, the P, 1 plus R over N to the N times T minus 1 times N over R, that was already determined in part A, where we had $66,438.85. Okay, so you got 1 plus 0.10 over 2. So this is going to be 1.05. Times 66,438.85. So for what we have in terms of the theoretical maximum, okay, you're going to have a 5% difference. In this case, this is going to be, I think, around some $3,300 more. In this case, we have $69,760.79. Okay. But in the case of real life, it's going to be somewhere in between these values. Okay, and the earlier the contributions on a consistent basis, the closer it's going to be to this figure. But if you were to have a habit of, just like putting in the $1,000 near the end of each cycle, say like waiting like 4 or 5 months, as opposed to getting it by the second month in the cycle, okay, you'll be closer to like the $67,000 range. So that's just the application that we have now. For what we have in the case,
Mr. Strickland.
Yes.
I'm sorry.
So
the P just disappears. Where does the P go?
Okay.
In that one.
Okay. For the 66,438.85. It's just sandwiching this whole thing here.
Oh, okay. I'm sorry.
That's all right.
Yeah, I see what you're saying.
Yep. All right. And we have now. Okay, so we're looking at future value, but now for 27. Okay, now this is where you're still looking at annuity, but where the future value is already determined. Okay, and here we got for number 27. Okay, it says here that for a child born this year, okay, it says a 4-year college education at a public university is projected to be roughly $170,000. And it says assuming a 5% rate of return compounded monthly. About how much must be contributed to a college fund every month in order to have $170,000 in 18 years. Okay, and it says note, okay, to use the regular annuity formula. Okay, and it says here that A is given, so we're looking at how much is to be contributed every month, and this is going to be referring to P. So you're solving for P, and whatever answer you get, you're looking at rounding up to the next penny. Okay, like if you have like 32.4 cents, just guarantee that the target is met, you're just going to round up to like 33 cents. And now, not the nearest penny, but to the next penny. Okay, if you don't have an exact cent amount in the calculation. All right, so we have for 27. Okay, and we've got for this setup. Okay, so let's go ahead and set things up here. We have for 27. Okay, you have $170,000 now. That is going to be the value of A. And we have a 5% rate of return. Okay, so you have R is equal to 5%. And now we have compounding to be done monthly, and you're looking at contributing every month. So N, you got the contribution as well as the compounding of interest. Okay, that's going to be 12 cases. So you have monthly. And for the time span, okay, we're looking at meeting the $170,000 goal in 18 years. And we're trying to figure out, okay, just what the value of P is going to be. All right, so taking what we have in the setup. Okay, so you have with 27. This is what we have provided. Okay, and referring to the annuity formula. Okay, so you have A is at $170,000. Have is equal to P, which we are trying to solve for. You have times the quantity. Okay, so you have for 1 plus R over N. So again, R we have at 0.05. And over N, which is at 12. And for N times T, so you have 12 times 18. And minus 1. And for times N over R, so N is at 12, R is at 0.05. So got P. Okay, now for what we're going to have inside the parentheses and the brackets. Now you're going to have a decimal that's going to repeat. And so for the figure on this one, okay, so you have 1.004, and you have 6 to be repeating. And for the exponent, you have 12 times 18, which will be 216. You can have minus 1. And 12 divided by 0.05. Okay, so this comes down to a whole number. So you have 240. And for the following steps, okay, quite a bit of number crunching to be done for this sum to the 216th power. Okay, so we're looking right at around 2.45, 2.46. And again, for this decimal, I'm going to take 1 away. Again, we're solving for p, so we're kind of setting the stage where we can determine about what p is going to be. Okay, so for what I have from the numbers in the brackets, okay, we have with our number here. I'm just going to go ahead and get the full display. And my figure has 1.455008,423. Times 240. Okay, so I have 170,000. And if I multiply 240 and this decimal number, so I have 349. Okay, it's got 349, just over 349.2. Now keeping all of these decimals, okay, because we're looking at rounding up to the nearest cent. Okay, so for what we're going to have, if I divide $170,000 by this decimal, you're going to have for a p. Okay, we have right at 486. You got 0.8. 2421, and again, now to the nearest cent, rounding to the nearest cent, so you'd be looking at 82 cents. But that's not the same as rounding to the next cent or to the next penny. So to ensure that there will be $170,000 on the basis that you will have 18 years of the same kind of activity on a monthly basis. Okay, we're looking at each contribution to be at minimum $486.83. So it's kind of like working in reverse. Okay, with raised retirement, okay, the contribution amount was already given and the final value was to be determined. But in the case of funding for $170,000 education plan, okay, $170,000, they have the end goal given, and you're asking, okay, how much the contribution monthly amount is going to be. So to ensure at least 170 grand, you're looking at putting in at least 486.83. All right, now for what we have among the items, okay, so there's a lot of interaction, okay, between exponential functions and logarithmic functions, and just kind of transitioning over to what we have for items. In chapter 8, we have just taking what we have and kind of going back to linear functions and equations. And we have in chapter 8, and we have what would be systems of equations. And for first part here, and I'm just going to call this systems of linear equations. And it doesn't have to be limited to just two equations, but for right now I'm just going to limit it to the variables x and y. Okay, so for a system of linear equations, say we have in two variables, say we have a of 1x plus b of 1y is equal to c of 1 for the first equation, and for the second we have a of 2x plus b of 2y is equal to c of 2. Okay, and for this system, okay, if there is one solution, it could be no solution, might be an infinite number of solutions, but if I have one solution, if there is one solution in the system, if there's one solution in this system, the graphs of these equations will intersect at the solution point. Which is going to be x, y. So you're looking at the values of x and y that will fit into both equations in the system. And now what we have in terms of specified cases, say for a two equation system, say if we're looking at solving for x and y, we'll say that for the first system, we're looking for the values of x and y, and we'll say such that 3x minus y is equal to 3. And also where we have x plus y is equal to 5. Okay, so we got 3x minus y is equal to 3, x plus y is equal to 5. And we could use like a process of elimination through what is often referred to as the method of addition. And if you notice, we got 3x and x for the first and second equations. And if you notice for y, we have a negative y in the first equation, positive y in the second, and you already have additive inverses with negative and positive y. And so what I can do here is that I have the capacity to add the equations and one might ask, okay, why am I doing this? Well, adding them, I'm going to have y eliminated, and this will create the opportunity for me to go ahead and solve for x. So I'm going to have 3x minus y is equal to 3. And I have again that x plus y is equal to 5. And if I add the equations, then I have negative and positive y to go out. So here I have 3x plus x is going to make 4x. And 3 plus 5 is 8. And if I solve for x, so we have dividing by 4. Okay, so I have that x is equal to 2. So I have half the solution with x at 2. And I can take 2 and put in place of x and solve for y. And I can choose either equation from the system to work with. And I'll just go with the second one. So in the process, okay, so I can plug in 2 for x and solve for y. So if I just choose this equation, but I could have chosen the first one. Go with x at 2. So I have 2 plus y is equal to 5. In this case, we had that y is equal to 3. You can always double check, so you have x at 2, y at 3, 2 plus 3 is 5, and also 3 times 2 is 6, minus 3, 6 minus 3 is equal to 3. So we have, in the case of the solution, okay, so if I draw out distinctly, okay, so you have x equal to 2, y is equal to 3, and if I were to put as an ordered pair, okay, we have the solution point is going to be at 2, 3. So that's saying that the graphs of these equations would intersect at that one point. Okay. So the first case is where you can arrive at least to the solution of one variable through the addition method, and then the second variable, again, just looking at substituting for the already solved variable. And let's say that if we have second case here, and let's say that where the method of addition is not quite so automatic. And let's say that for this system, we can say that we have x plus 3y is equal to 5, and where we have 3x minus 2y is equal to negative 18. Right, so I have this system of equations. And if you notice, we do not have additive inverses. Okay, have x and 3x, no elimination if I add directly together. And while I have positive and negative y terms, once again, we have 3y and negative 2y. They don't cancel each other completely either. And what you can do is that in this particular situation is that we can eliminate either x or y and solve for the other variable. In other words, by rewriting either or both equations. Okay, now the first case I was able to eliminate y, but things were already arranged where I could just keep the equations as they were. But now I can rewrite this equation where I can eliminate either x or y terms through either adjusting the first equation or second equation or both equations. So, but I think what I'm going to do here, and I think this is going to be the simplest route. Okay, we have with the x terms, I have x and 3x. Okay, now if I were to eliminate the x terms, okay, now you've got 3x, okay, has a higher absolute value coefficient, and I can adjust x to where I can get the 3x eliminated, but there has to be an adjustment with the first equation. Okay, so what is going to take out 3x? It is not going to be x or negative x, but negative 3x. So if I'm looking at, say, eliminating the x terms, what I can do is I can multiply the first equation by negative 3 while leaving the second equation untouched. So if I multiply the first equation by negative 3, we have negative 3x minus 9y is equal to negative 15. And keeping the second equation untouched. Okay, so I can add the equations together. And for what we have now, so got negative 3x plus 3x. These terms go out. Negative 9y and negative 2y will become negative 11y. And we have negative 15 and negative 18 will be negative 33. And I can go ahead and solve for y. Okay, so we have for y itself. Okay, so y is going to come out to 3. So I have half the solution. Okay, where I have, once again, y is going to be at 3. And what I can do is I can go back to the system and solve for x. Okay, so I can plug in 3 for y in either equation from the system. Then we'll go with the first instance. I already have x present, but I could do it with the other. So plug in 3 for y. And solve for x. Okay, we'll go with x plus 3y is equal to 5. Okay, so I have x plus 3 times 3 is equal to 5. Then we have the x plus 9 is equal to 5. And from this, okay, we'll have the x is equal to negative 4. And so just looking at what we have for the results to check for at least the consistency. Okay, so x is negative 4, y is at 3. 3 times 3 is 9. Negative 4 plus 9 is 5. With x at negative 4, and again, y at 3. We got 3 times negative 4 is negative 12. Negative 2 times 3 is negative 6. Negative 12 minus 6 is equal to negative 18. So those values of x and y will work for both equations. So we're going to have for the solution, okay, so we can say we have x is equal to negative 4 and y is equal to 3. And again, if you were to display as an ordered pair, we have for the points, we would have negative 4, 3. Okay. Now for both examples, okay, I had like the x and the y terms on the same side of the equation. And that might not always be the case. And there are some alternative methods that might be used outside of the method of addition or elimination. And this is what we have for what could possibly be referred to as the method of substitution. And just as an example, okay, say again, if we're looking at solving for x and y, and we can say that, let's say if I have okay, solving for x and y, I'll say that for this system, I'll have the first equation would be given in terms of the slope-intercept form. So I'll just say that we have y is equal to 4x plus 3 They have the x and the y terms apart from each other, and we're still looking at the same values of x and y, where also you're going to have the x plus y is equal to 13. Okay. So you're looking at the same x and y values that will ring true for both of these equations. So just looking at what we have now. Okay, first equation, we have y isolated. We have y is equal to 4x plus 3. And again, I have x plus y is equal to 13. Okay, now where the substitution comes in, okay, from one equation, if I have a variable isolated, I can substitute for that variable in the other equation. And what I mean by this, for y is equal to 4x plus 3, guess what? Y is going to be the isolated variable. And that which is isolated, I can substitute for in the other equation. So what I mean by this, you got y is defined as 4x plus 3. and that which is isolated I can substitute for in the other equation. So here I can take the x expression that defines y and substitute y in order to solve for x first of all. Okay, substitute for y, solve for x. And if I do this, okay, so I have x plus, in place of y, okay, so I have 4x plus 3. That is equal to 13. And I'm using the parentheses just to signify that this is what I have replaced y with. And this is with the defining it as 4x plus 3 from the first equation. Okay, so upon adding together, okay, so we have x plus 4x is going to make 5x. Okay, so you have 5x plus 3 is equal to 13. And for what we have in following through, so take 3 away from both sides. So we have 5x is equal to 10. And with division by 5, we'll have the x is equal to 2. Okay, so you have half the solution with x at 2. Okay, and with x determined, okay, I can now determine what y is going to be, and it's going to be through plugging in 2 for x in either of these two equations. Okay, x is solved for it, and now I have the capacity to solve for y. Okay, so plug in 2 for x. And solve for y. Okay, so y is equal to 4x plus 3. Okay, so the y is equal to 4 times 2 plus 3. Four times 2 is 8, and 8 plus 3 comes out to 11. Okay, so I have x at 2, y at 11. I can always go back and check. So if x is 2 and y is 11, well, we've got 2 plus 11 is equal to 13. With y is equal to 4x plus 3, again, we got 4 times 2 is 8, 8 plus 3 is 11, and y is equal to 11. So these values do check out. And so we have for the solution, okay, so we have x equal to 2, and y is equal to 11. We have with the ordered pair, so this can come out to 2, 11. So the graphs of these equations would intersect at that ordered pair. Okay. And again, there will be different types of systems, and you can have also the result to consist of more than just one point in the solution. And let me kind of cap things off, okay, where we might have a system of nonlinear equations. And let me give you just remaining example. And let's say that we have say if I have as a system of nonlinear equations, And say if you're looking at solving for x and y, and we say that for what we have in x and y will be such that if you take the sum of the squares, we're going to have 61. And also, if we have the difference of squares, like we have x squared minus y squared, this will be 11. So you're looking at the values of x and y such that the sum of the squares will be 61, and where the difference of squares will be such that x squared minus y squared is equal to 11. Okay, now I already have additive inverses with positive and negative y squared, so we can go ahead with the method of elimination or the method of addition. So in this one, okay, so now x squared plus y squared, okay, is equal to 61. And I have x squared minus y squared is equal to 11. And if we look at adding the equations together, so that positive and negative y squared will go out. And x squared plus x squared is 2x squared. 61 plus 11 is 72. And with division by 2, now we got that x squared is equal to 36, and I'm looking at solving for x and y. Okay, so I got x squared is equal to 36, and I could express as a quadratic equation in standard form, but what I'm going to do here is just use the square root property of equality. So just going from x squared to x, and where I have x equal to plus or minus the square root of 36. Okay, so we have two solutions for x, one positive and the other negative 6. All right, and looking at solving for y. Okay, and so I have both equations with x squared. Okay, and so for what we have in this particular instance, okay, so I can take either equation and just plug in 36 for x squared and if I do this, okay, so we've got x squared, okay, so that's going to be 36. Yeah, 36 plus y squared is equal to 61. And if I take the difference, subtracting 36 from 61, I'll have that y squared is equal to 25. And just as I went from x squared to x, I'm going to go from y squared to y. Again, utilizing the square root property of equality. So we have y, plus or minus, okay, the square root of 25. And so we had that y is equal to plus or minus 5. Okay, so we will have, at least in the case of the solution set, okay, just kind of using compact notation, you have x equal to plus or minus 6, and y equal to plus or minus 5. And if I were to express as ordered pairs, so you have like one combination where both x and y are positive, two combinations where I have one positive, the other negative, so you have like 6, negative 5, as well as negative 6 and 5. And we have with the remaining combination, okay, so we have negative 6, negative 5. Okay, so I have 4 solution points. Yeah, so I got x squared plus y squared is equal to 61. So we have a circle that is formed with the center at the origin. Now for x squared minus y squared equal to 11. Okay, we have what's referred to as hyperbola. Okay, and the points of intersection will be the solution sets for what we have in x and y. So we have at this point, I got negative 6, 5. Another intersection point where we have both x and y negative, so we have negative 6, negative 5. And the solutions where x is positive, we got x at 6, y at negative 5. And also we have where x and y are positive, respectively at 6 and 5. Okay, so this is just a visual construct of how the solution to this system of equations will appear.